This is all rehab lecture 3, part 4. I have to make one quick correction to slide 12 of lecture 3, part 3. So let's do that first, and then the rest of the slide set will deal with speech understanding and the audiogram. And really sort of the distribution of speech energy on the audiogram is really a better title. All right, so first thing though, on slide 12, lecture 3, part 3, I had described in words, I'd listed on words, the words saucer-shaped incorrectly. Slide 12 should read worse hearing in the middle frequencies, not better. And so here's a revised, corrected slide 12. So you see at the bottom it says saucer shape as hearing is generally worse in the middle frequencies. Now the illustration here, so slide 13 from part 3 was correct. So there was the problem was I just had the incorrect wording on that slide 12. So again, remember that audiogram is shown as the lesser numbers is better hearing, poorer numbers, bigger numbers is poor hearing. So here's the lower frequencies, relatively better. Here's the higher frequencies, relatively better. And then what do we have kind of in the middle are these in this audiogram at around 65 dB, so that would be relatively poorer, relatively worse relative to the lower frequencies at 40, or the higher frequencies also at 40. So I stand corrected. All right, so in looking at the audiogram, basic question is, are we able to sort of get a prediction of how well someone's going to understand speech based on an audiogram? And the general answer is no, or at least it's very, very difficult to. Because the audiogram itself is not a predictor of a great predictor of speech understanding ability, in audiology we have to do other tests for it, speech understanding. In fact, a test called monosyllabic word recognition is the typical name of the test that we would do, sometimes referred to as a speech discrimination test. Although it's best described as a monosyllabic word recognition test. That's the psychometrically most correct way to say it. So an audiogram, while it doesn't always tell us how a person's going to understand it is going to provide us with some fundamental knowledge about what their capability to understand may be. And it's based on the notion of audibility. So while there are many factors that are going to determine whether or not and how well someone understands speech, okay, primarily the nature of the person's auditory pathology. So if a person has auditory pathology that's centered in their inner ear or along their auditory nerve, it's very, very likely that their speech understanding ability is going to be compromised. That's just the way the pathology typically is manifested. All right, so pathology is going to be one of the major factors. But if we just think about it from just how do we, even people with normal hearing process speech, the first stage is audibility. The first stage is we have to be able to hear it. So audibility is just another word for can you hear it. So the point here that I'm trying to make as we get started is that audibility alone, while it's important, is not going to be a guarantee that a person's understood, because again, audible sounds to someone who has significant pathology. So if they have a pathology in, again, their inner ear auditory nerve, pathology, thank you, then in that case, then that's going to make the understanding of speech very poor. So, but we do think that it's going to be an important first step. And basically on the audiogram, that's what we are able to sort of have a better handle on, is what's in fact audible to the person. So the audiogram will give us that. They give us the first step. All right, so when we think about then the distribution of speech sounds and how that relates to the audiogram, we're sort of talking about a topic called speech acoustics. Now, I'm not sure in your earlier classes where you got this, if you got it. So I'm going to do a little bit here through these part 4, part 5, and then in lecture 4, I'm going to make sure that I'm satisfied anyway that you've had some exposure to speech acoustics. So we're going to do that over the next, the remaining lecture 3 and then lecture 4. So here's a figure from the director of auditory research from Bell Telephone Laboratories in the 1900s. His name was Harvey Fletcher, very influential relative to speech communication and sort of just the basic physics and acoustics of speech. This is not an audiogram, but simply a scientific chart. These are units of decibels, really, and this is now ascending decibels. This is greater amount of decibels, so that means that 100 units here, 100 dB, for all intents and purposes, we can call these decibels. 100 dB here, 70 dB, so 100 is much stronger than is 70. This is frequency as we've typically been looking at it, except these are not in the octaves we're used to seeing. They are in octaves, because octave is doubling of frequency, but not along the octave organization we're used to seeing. So again, what we're seeing is over here, any of these sounds in here, these are going to be the most intense, the most powerful sounds, and we're going to talk about them more in the next lecture set. But essentially, in our generalization right now, essentially these sounds are going to be most of the vowel sounds, and so this chart's not IPA. As we go to the weaker sounds, this is going to be weaker sounds over here. We're going to see sounds like the SH and the TH and the S. The P and the T and the K. So most of the softer consonant sounds, actually the reason they're softer is they have less energy in them. So that's part of their acoustic profile. So again, all sounds are going to have from a speech acoustics point of view, will have a distinct pattern of frequency, amplitude, and duration. And every speech sound that we produce and utilize in whatever language is going to be unique relative to its frequency, amplitude, and duration. Now, this is a figure out of your book, and essentially this figure basically is just a redo of the chart that I showed you just a moment ago. So here's that Harvey Fletcher, from that same book that he did in 1953. Now, these are this is a list essentially derived from that chart I showed you. This is in IPA, an International Phonetic Alphabet, so you probably had that in your phonetics class. So you know that this sound over here, that symbol, is the sound that we would say in English as aw, as I might say in the word awful. If you're a native California speaker, you say awful, and that's not the same vowel as this. So my Eastern Seaboard aw, awful, coffee, talk, dawn. I don't overpronounce it like that usually, but you get the idea. That's that vowel. The weakest sound that we have is the voiceless TH sound, as in the word thin. Now the relationship between, this is in kind of odd units, but the relationship of the strongest sound, the aw, to the weakest sound, the th, is 680 times to 1. That turns out to be, and just trust me on the math here, about a 28 decibel difference. And so then we can say that sort of the range of typical powers of sounds is about 28 decibels. So that's a reasonable number to kind of keep in mind. So when we think about this notion of audibility, we have to kind of think about how does this relate to understanding. First of all, audibility is not the same as understanding. It just isn't. That's why I got this big not equals to. All right. But audibility is important to understanding. Audibility is the fundamental stage prior to understanding. So what we're going to have a sense about is in sort of the reception of speech sounds, what frequency ranges contribute most to understanding. Now, if we look back a couple of slides, you're going to see that the strongest sounds in English were the lower frequencies. So therefore, if I said to you, well, of all the frequencies, which ones are the most important for understanding speech, not for detecting it, not for audibility, but what sounds are the most important for understanding speech, and you looked at that slide I showed you a moment ago, you probably would have drawn, maybe correctly so, the idea that, well, that must be the lower frequencies because they're the most powerful. And if you said that, you would be wrong, because, as I'll show you here in some other studies from Bell Telephone Laboratories from Harvey Fletcher, it turns out that the higher frequencies, which we'll operationally define as higher than 1,000 hertz and higher, contribute the most to speech understanding. And conversely, and maybe paradoxically, the frequencies below 1,000 hertz, although they're the most intense, contribute the least to the understanding of speech. And that's something you just have to kind of remember and kind of work through. Now, this particular finding was demonstrated also by work at Bell Telephone Laboratories by a couple guys named French and Steinberg. Now, they worked for Harvey Fletcher at Bell Labs. Remember, Fletcher was the head of auditory research at Bell Laboratories, and Bell Laboratories was the telephone company. So they had a very strong financial interest in determining that their equipment could transduce and transmit speech energy. So in a series of studies that involved filters, they took energy away from speech and had listeners try to repeat back words. And so essentially in something called a low-pass, high-cut filter, what you're basically doing is you're cutting the higher frequencies. So if someone heard all of the energy, let's look at the top line here. If you were able to hear all of the energy out through 7,000 hertz, you get 98%. Now, if we started to cut some of those high frequencies, and so we progressively work down the list here, and we get to all that we're going to let you hear is through 500 hertz, meaning we're going to high cut everything above 500 hertz, you'd get a score of 5%. If I allowed you to hear everything through 1,000 hertz, you would understand 27%. That's just the nature of this kind of filtered speech test. On the other hand, if all you heard were the frequencies from about 1,000 hertz and higher, and you cut everything below was cut, you would still understand at a rate of about 69%. So, point being, low frequencies contribute relatively little, high frequencies contribute relatively a lot. This same slide, the same data from that slide are shown here. And again, just trying to make the point that here's that low pass, high cut one at 20, whereas if all you heard was through 1,000 hertz, your score would be 27%. So 27% if all you hear is through 1,000 hertz. And then again, this low cut, high pass. So if everything you hear is above 1,000 hertz, you'd hear it approximately 90%. And hope I'm saying this correctly. This is all in percents correct. So hopefully I'm not confounding decibels and percentages. In a sort of a table that kind of puts these two sets of numbers together, we've got the idea here that there are different ranges of intelligibility is another word for understanding. And let me go back here. Sorry, I did that. So intelligibility is another word for understanding. And so what I just showed you a moment ago is at 5% if you could hear through 500 hertz. And so there's different ways of kind of thinking about it. If all you could hear is above 1,000 hertz, you would hear at around 90%. And this is just a way to kind of show you, if anything else, the premise, the basic value of this little table, rather than the little minutia in it, is if all you can hear are the low frequencies, you're not going to understand very well. Okay? And if all you can hear are the higher frequencies, you'll understand very, very well. Conversely, most of the power of speech is in the lower frequencies. So here's 95% of the power of speech is in the lower frequencies. Very little of the power of speech is in the high frequencies. And we inferred that from that other slide. All right, so one way that we can kind of think about how can we look at the importance of speech frequencies to their contribution to understanding is to kind of take that information and create, add mathematical weights to the different frequencies. And that general sort of engineering mathematical kind of approach to this created something that might seem sort of a weird name to you, and with an emphasis in speech-language pathology, but something that's just referred to as an articulation index, and we're going to just abbreviate it as an AI. This particular mathematical treatment we can usually show as an overlay on an audiogram, but it gives us a representation of how valuable particular frequencies are to understanding. So in a more or less recent 1990 clinically consumable, treatable aspect of this, these two guys, Muller and Killian, came up with this idea of showing the AI distribution. There's that AI, the AI distribution shown in this statistical envelope. The basic premise here is that there's 100 dots in this form, and each dot counts 1% toward intelligibility. So depending on where the person's audiogram is, you can kind of get a sense of what their audibility would be. Again, audibility being the first stage to understanding. And so with an AI overlay, you can have a sense of, again, what's audible to the person. Now, again, it doesn't tell us exactly what they're going to understand, but it kind of just does tell us the frequency region, and then we have to kind of put some more stuff in there to make more sense about it. So the basic idea is where the person's audiogram kind of crosses through the region, crosses through this little grid. You count all the dots that are in the higher amplitudes there. That's what they hear. And the lower dots above their audiogram, they don't. That's what we're going to do when we get to part 5 of this. So here's the more recent treatment of this count the dots audiogram. Moeller and Killian came back and did it in 2010. And it looks essentially the same sort of idea. But the basic idea is that if a person like you or me hears at this level, then we're able to get all of these, and so we'd have an AI of 100. And again, we'll do some more examples as we get into the next slide set, part 5 of the slide set. The last one here, just to kind of summarize this, is that when you get this AI, you're getting an engineering number that tells us more or less a percentage of what the person's going to be receiving. And that percentage is weighed against the relative importance of those frequencies to the audibility of speech. So usually we see this as a percentage, or sometimes it's given as a decimal point in the literature. But again, it's giving us a weighed sense of how much is available to the listener. On that note, we will move now to part 5 and show some examples.